In my previous session, I have told you what is the difference between orbits and orbitals, shells and subshell. Now it's time to see how electrons are getting filled up in orbitals of atoms. Now, for example, the P subshell, it contains orbitals like px, py, pz. So when I am telling a p1 configuration, a p2 configuration, how will those electrons be filled up? Will both the electrons be in the same orbital? Will it be in same? Suppose I say it is P2. Will it be PX2 or will it be PX1, PY1 or what is it? So it is time to discuss about filling of electrons in orbitals of atoms, which is governed by rules, by laws, by principles. So let us discuss the principles of filling of electrons in orbitals. Hello everyone. Our today's topic is filling of electrons in orbitals. So, how in the orbitals the electrons are filled, that we are going to see. What are the rules, what are the principles, that is what we are going to see now. In Pauli's exclusion principle, I started with Pauli's exclusion principle because our previous module was on quantum numbers. So here it says that no two electrons in the same atom can have the same set of 4 quantum numbers. That means ये दो इलेक्ट्रॉन कोई ऐसा नहीं होगा जिसका ये 4 क्वांटम नंबर सेम हो. ठीक है. So electrons in an atom are described by 4 quantum numbers और वो quantum numbers कौन कौन से है? Principal quantum number n, that shows the shell number or the energy level. Azimuthal quantum number L, that shows the subshell and the orbital shape. Magnetic quantum number, that shows the orientation of the orbital. And spin quantum number, that gives the direction of the spin, clockwise ho ya anti-clockwise ho. It can be either plus half or it can be minus half. All these things we have seen in the previous section. Now, according to Pauli's principle, if 3 quantum numbers are the same, the fourth, the spin quantum number must be different. That means, agar n, L or ml same hai, that means this ms factor, the ms quantum number must be different. That is, only 2 electrons can occupy the same orbital with opposite spin. So if I say this is one orbital, say here they are telling 1s, so I'm telling 1s over here. So if it is 1s1 configuration, then obviously it will occupy only 1 electron will occupy the 1s orbital. But if it is 1s2 now, what will happen? It will be 1 electron in spin up, the other electron in spin down. For this reason, we are drawing half arrow. That means half spin and half spin in opposite direction. Plus half and minus half, it shows. So this is 1s2 configuration. Maximum 2 electrons can exist. Now, here we can see the distribution of electrons in different energy levels and their quantum numbers. See, if n is equal to 1, this n is equal to 1, it's the K shell. K shell can have L values 0, for which ml is 0, and the 2 electron can have ms plus half and minus half. So how many? See, subshell designation is 1s. This the same thing I had written in the previous video. Here it is 1s. and in the subshell total number of electron is 2 and n is equal to 1 has only one value of L. That's why it has only s orbital. That's why in the energy level also there are 2 electrons. Now n is equal to 2, that is L shell. There the values, shell is L, there the azimuthal quantum numbers can have values 0 and 1. Why? Because L can have values 0 to n minus 1, 0 to n minus 1, and ml can have values plus L, 2 minus L, including 0. Okay, so that is the recap of what we have seen in the previous video. So now L is equal to 0 and 1 for n is equal to 2. That means L is equal to 0 means s orbital or s subshell, and L is equal to 1 means p subshell. Now p subshell can have 3 degenerate orbitals. Why? Because it has 3 ml values, plus 1, 0, minus 1. That corresponds to px, py, pz. Each orbital can accommodate maximum 2 electron with opposite spin, plus half, minus half. So s orbital 2s can have a maximum of 2 electron because it has only one orbital. It is one orbital. So p subshell has 3 orbitals. So for that reason it can have maximum of 6 because each orbital can have 2 electron. So total number of electrons in the energy level n is equal to 2 is 8. 2 plus 6, 8. So now the third one, n is equal to 3, third shell, that is the M shell. It can have L values 0, 1 and 2. And ML values will be for 0, it is 1, only 0. So this is S, this is P and this is D. So remember always that P is triply degenerate. So there are the ml values plus 1, 0, minus 1. D can have plus 2, 2 minus 2, including 0. So there are 5 set of degenerate orbital. In each orbital, maximum 2 electron can be there. So 5 into 2, 10 maximum electrons can be there in the subshell D. And corresponding to n is equal to 3, so 3D. So in n is equal to 3 shell number, how many total electrons can be there? For that, you have to see what are the subshells corresponding to the shell. That is what? That is S, P and D. So n is equal to 3 shell can have a total of 2 plus 6 plus 10, that is 18 electrons. So next, there is a question over here that I have put for you. Which of the following sets of quantum numbers is not allowed? Justify. Now, not allowed means you have to check with which principle? Pauli's exclusion principle. From there, you have to see that whether there are any quantum number out of the 4 which is same or not. Okay. Now just see, let us check what it is. See, n is equal to 2, first option. L is equal to 1. So n is equal to 2 can have values of L. It can have values of L as 0 and 1. So here it's 1 means P. If it is P, then M can have value 0 and plus half. Fine. Now n is equal to 3, L is equal to 0. That means I'm talking about B. N is equal to 3, L is equal to 0 means 3s. Now 3s, ml values for s should be 0 only. Here it is m is equal to 1. See, when here it was L is equal to 1, ml can have values plus 1, 0 and minus 1. So ml value equal to 0 was allowed. But here if L is equal to 0, for this ml can have value only 0. So this is not allowed. Okay. So it was not same set of quantum numbers. It is the concept on magnetic quantum number. Okay. Next. Question number 2 that I had selected. How many electrons can have the following set of quantum numbers? That is, n is equal to 3 and L is equal to 2. How many electron can have? See what it is. See, I said 10 electrons can have n is equal to 3 and L is equal to 2. How? When I'm telling n is equal to 3, L is equal to 2, L can have values 0, 1, 2 corresponding to S, P, D. So this is a D. This is a D subshell. So it's 3D. See, it's 3D subshell. Now for L is equal to 2, magnetic quantum numbers, ML values can be minus 2 to plus 2. 5 values can be there. So 3D can have maximum 5 into 2, 10 electrons, because each orbital can have, these all correspond to each orbital. So like that there are 5. So they can have in total 10 electron. I hope it is clear. Next, moving on to question number 3. State whether the following 2 electrons can exist in the same atom or not. I have to justify. I have said first electron A, n is equal to 2, L is equal to 1. That means what? It is 2p. Second electron, n is equal to 2, L is equal to 1. That is also 2p. Both are in 2p. And both are in the same magnetic quantum number. But they are having opposite spin. Yes. That means the fourth quantum number is different. So yes, they can exist. Okay. So next, moving on to Aufbau principle. The Aufbau principle is a fundamental rule used to determine how the electrons will be filled up in the orbitals. Now people ask, ma'am, what is Aufbau? So the meaning of Aufbau is building up. That means how is the configuration, electronic configuration of atoms built up? It is built up in increasing order of energy. So lowest energy orbital upward. That means in increasing order of energy. Increasing order of energy, it is electrons are filled up from a lower energy orbital to a higher energy orbital. So electrons are filled in atomic orbitals in order of increasing energy from lowest to highest. So saying that is not enough, so I have shown how it is filled up. Order of orbital filling. This is not always in the simple order of increasing principal quantum number n. That is, it is not always n is equal to 1 will fill up first, 2 will fill up next, 3 will fill up next and 4 will fill up next. It's not like this. 1 and 2 doesn't have problem, but let us see where the problem lies. Because there are orbitals where overlap in energy occurs. Energy is comparable. There is not much difference in the energy of orbitals. So it is not always in simple order. Why? Because some orbitals overlap in energy. They have comparable energy. Here it is 2s, 2p. 1s, 2s, 2p. Just see 3s, 3p. But over here you see after 3p comes 4s and then 3d. So 4 has entered. So 4s, 4p, 4d should be there. But after 4p, there is 5s occupied first and then 4d. There is 6s occupied first and then 4f. So we can see this, it is going on in this manner. So there is something which tells that, of course, according to Aufbau principle, that means the energy of 3p is less than the energy of 4s, is less than the energy of 3d. This is the energy order. That's why it is filled up in this manner. Now, here the diagonal rule shortcut is given. How? This is the diagonal rule shortcut. See how it is being done. First 1s, and then it goes and 2s, and then it goes and 2p 3s. This is 3p 4s. This is just to remember. This is just to remember how the order is. But actually it is governed by a rule which is Madelung's rule, or known as N+L rule. Says what? That whichever electron or the energy of orbital, it depends on the summation of the principal quantum number and the azimuthal quantum number. And electrons are filled up in increasing order of N+L values. That means lower value of N+L will be filled up first, followed by higher value of N+L. Okay, so the energy of an orbital depends on sum of n, principal quantum number, and azimuthal quantum number. Lower N+L value, lower is the energy of the orbital. That's why it is filled up first. If two orbital have same N+L value, the one with the lower n is filled first. That is the reason that over here you had seen what had happened. 3p was filled up before 4s. Why? Let us see. For 3p, what was the n value and what was the l value? N was equal to 3 and l was equal to 1. And so what is n+l? N+l is 4. And for 4s, it was what? It was n is equal to 4, s is, l is equal to 0, again n+l is 4. So I said that orbitals having lower value of n+l will be filled up first. 3s में क्या हुआ था? In 3s, n is equal to 3 and l is equal to 0, and so n+l was equal to 3. So 3 is less than 4, n+l. So for that reason, 3s was having lower energy than 3p. So there was no problem. But 3p and 4s, they are having the same value of n+l. For such case, the orbital with a lower value of n will be filled up first. It has lower n value, and so it will be filled up first, and so the energy of 3p is less than that of 4s as per n+l rule. So let's see, again proceed. So the quantum numbers reminder, that is what I said. N is the principal quantum number indicating the shell number. L is the azimuthal quantum number indicating the subshell. So that is what I said. If it is S, then L will be equal to 0. If it is P, L will be equal to 1. If it is D, L will be equal to 2. If it is F, L will be equal to 3. Now this N+L rule governs the energy order and the order of filling electrons. So we can see that this is the orbital N, L and N+L, and this is the energy order which it will be filling up. So here it is, we can see 4s and 3d. 4s and 3d over here. It was having, see, 3p, n+l, which will be filled up first. See, first, second, third, fourth, fifth, sixth, seventh, eighth. This was based on n+l value. If the two n+l values are same, for what we saw, we have seen, okay, first pay your attention over here. N plus L value same for 3p and 4s. Okay. So the one with a lower value of N will be occupied first. So 3p is occupied first. So energy order, this is 5th and this is 6th. Previously also we had N plus L equal to 3 for 2p and 3s, and there 2 was less than 3. So 2p was having lower energy than 3s. Again we are having C 5 N plus L having 5. So it is filled up in increasing order of N. N is equal to 3, N is equal to 4 and N is equal to 5. So this is how N plus L rule is followed. Now that is the same thing that I have explained. 4s has N plus L equal to 4 is filled before 3d, where N plus L is equal to 5. So increasing order of N plus L value. Though the principal quantum number 4 is greater than that of 3. Now for 3p and 4s, both have N plus L equal to 4. So you have to choose the one with the lower N. So 3p comes first, and so it has lower energy than 4s. Okay. So now Hund's rule of maximum spin multiplicity. Here Hund's rule says what? That it is one of the key principles used to determine how electrons are arranged within orbitals of same subshell. Why same subshell? Degenerate orbitals having equal energy. So electrons occupy all the degenerate orbitals singly before any pairing occurs. Suppose I say that I want to fill up in P. It can be 2p, it can be 3p, any. So NP I am writing. So if it is P1, then it will be having one electron. If it is P2, then it will be occupying the next orbital. This is the shell, and these are the, say, +1, 0, -1. These are the ml values, or these are the orbitals. So electrons will be singly occupying the orbitals. If it is P3 configuration, the next electron will enter here, but all will be in spin up condition. Until and unless all are filled up, there cannot be any pairing. Suppose I'm talking about NP4. Then what will happen? This will be 1, 2, 3. The fourth will be occupying here. And so these will be like this. So here what has happened? Here actually MS value is +half and -half. 2 electrons present in the same orbital, fine, but they are having opposite spin. So what is the maximum possibility of accommodation in the p shell? See, if each orbital can accommodate 2 electron and there are 3 set of degenerate orbital, then maximum accommodation is 6 electrons in the p subshell. Okay, here this is subshell. Okay, now in other words, every orbital in a subshell is singly filled with 1 electron before any orbital gets a second electron, and all singly occupied orbitals have electrons with same spin. That is what I have shown here. Why is it so? Electrons are charged, negatively charged. They repel each other. Keeping them unpaired in different orbitals of same subshell minimizes the repulsion and increases the stability. That is the reason why this is happening. That is the scientific reason. We should know why it is happening. Electrons with the same spin, either spin up or spin down, also tend to stay further apart due to the quantum mechanical exchange energy. Okay, so now let us see an example. Nitrogen with atomic number 7. How do they occupy the electrons? Nitrogen, atomic number 7. Electronic configuration is 1s, 2 electron, because s can accommodate maximum 2. So after n is equal to 1, say this is n is equal to 1. then it is n is equal to 2, n is equal to 2, n is equal to 2 can have what? It can have 2s and it can have 2p. It can have 2s and 2p, and n is equal to 1 can only have 1s. So what happens? This is the increasing order of the energy of the orbitals. Now atomic number 7 means first 1s is having lower energy. It will be completely occupied. So 1 and 2. Then 2s will be 3 and 4. After that we have 2p orbital where it is triply degenerate and can have maximum 6 electrons, but 4 electrons are already occupied here, so it will be 1, 2 and 3 singly occupied, and we can see it is half filled configuration. Why half filled configuration? Half filled electronic configuration? Because the 2p subshell can accommodate total 6 electrons, 2 electrons in each orbital, and so it is having 3 electrons, which is half filled. 2p has 3 orbitals, so each can get 1 electron any pairing before any pairing happens. So all are in spin up, giving maximum spin multiplicity value. Okay, so the one which I have done over here, this one is the energy level diagram. That's why I have explained what is energy level diagram also. An energy level diagram is a graphical representation showing how electrons are arranged in an atom based on increasing order of their energy levels, shells and subshell. See, here what I have shown is shell, and here what I am showing is the subshells as well. P, in case of P, you can see that subshells. So it gives you a visualization of how electrons are filled in atomic orbitals. Now, how to fill? First, see the energy level, N. You have to see N from higher, that means lower to higher energy, it will be filled up. See the subshell L. That is how I had worked out. See the subshell L. See, N is equal to 2 can have L values what? It can have L values 0 and 1, S and P. So there was 2S and 2P. That is what it was done. Okay, so after that you have to fill, keeping in mind that each orbital can have maximum 2 electron, but each subshell over there can have total, depending on how many degenerate orbitals are there. P has 3 orbitals, so the P subshell can have maximum 6 electron. D subshell can have maximum 10 electron because there are 5 set of degenerate orbital, and these 5 set of degenerate orbitals can have 1, 2, 3, 4, 5 singly occupied, then pairing 6, 7, 8, 9, 10. So it can have a maximum of 10 electrons. And the way I am filling up, in the same way you are going to fill up the electronic configuration. In case you see that any orbital is having a single electron, then you go and make it complete arrow. F has 7 set of degenerated orbitals, and so it can have a maximum of 14 electrons. So Aufbau principle was it's just a recap of it. Pauli's exclusion principle, Hund's rule, recap of it. You have to follow in the energy level. See, when I am doing the energy level diagram, I am following all the rules, be it Pauli's exclusion principle, be it Aufbau principle, or Hund's rule of maximum spin multiplicity. Okay, now after this was an example where I was trying to show you oxygen having atomic number 8. So atomic number 8 means first N is equal to 1 will fill up with L value 0. N is equal to 2, L value 0 and 1. So this is 1s, this is 2s, this is 2p, and let me see. Here 1s can occupy 2, 2s can occupy 2, 4, 2p, 5, 6, 7 and then pairing 8. So this is how you are going to draw the energy level diagram. So next I have shown you the electronic configuration, how to write the electronic configuration following all the rules. See, atomic number 1 to 20 over here is shown first. Here you have to keep in mind, see, after each 1s1, 1s2, hydrogen, helium, you have to remember this. You have to remember the order of the elements. Okay, if 1s is filled up, then it goes to 2s. When 2s is filled up, goes to 2p. When 2p is filled up, goes to 3s, like this. It goes on. Okay, so just see this neon 10 is having completely filled orbitals. 1s is complete, 2s is complete, 2p is also complete. So how many electrons it is having? It is having completely filled orbitals, and the highest value of n is the valence shell. Highest value of n is the valence shell. And you see here highest value of n is equal to 2, and it is having 2 plus 6, which is equal to 8 electrons, and so it is having octet configuration. So neon is a noble gas. See, helium has duplet configuration. This is known as duplet configuration because it has only one s orbital, which can have a maximum of 2 electrons. After this you have argon. Argon 18, atomic number 18. So here you see argon can have 1s2, 2s2 and 2p6. So 2p6 is written as 2px2, 2py2, 2pz2, and it goes to 3s, n is equal to 3. So 3s2, 3 and 3p6. So it's totally, I will say, filled up. Now here again the valence shell is n is equal to 3, which has octet configuration. So these are the noble gases, and now I am showing you the 3D series. These are the D series, because here you see D1, 3D1 to 3D10. So these are known as 3D series, and it is known as first transition series. Why? They are the transition elements, and in the periodic table they are located in between S and P block. So here 3D1 configuration, 3D2, 3D3. Now where is 3D4? This is an exceptional configuration of chromium where it has 3D5 and 4s1 configuration. In order to give half-fill stability, and they have comparable energy 3D and 4s. So half-fill stability we can see here. What has happened here? Chromium could have 3s2, 3p6 and 3d4 configuration, right? But there was comparable energy between 3d and 4s. So in order to, and of course here let me tell you 4s2 was also there. So what has happened, in order to give stability to the electronic configuration, automatically to lower the energy of the system, the 3d gets an electron from the 4s and becomes half filled and 4s1. This is the electronic configuration of chromium, for chromium. Same thing we will see in case of copper. See, copper also 4s1 and 3d10, we can see 4s1, 3d10 instead of 3d9 and 4s2. Here it was, in chromium it was half filled, and here it is fully filled stability, fully filled electronic configuration stability. And zinc is actually not considered to be the transition. Why? Because it is having fully filled orbitals. We will deal with this concept later on in the later units. Now here again, it is the matter I want you to read a bit on your own, where you see that explanation of why the half-filled and fully filled configurations are more stable, extra stability is there. See, the example was given of chromium, example was given of copper. Okay, so now the configuration is here. In case of chromium, we have already seen 4s1 and 3d5. So this is what? This is 4s is occupied first, 4s1, 3d5. And here what is it? 4s1 and 3d10. Okay, so reasons for the extra stability, this is what I have jotted down. It is due to symmetry, due to exchange energy, and due to lower electron repulsion. Symmetry, when I talk about half-filled configuration, fully filled configuration, they are having an extra symmetry factor, and symmetry always gives stabilization. Exchange energy, more unpaired electron with parallel spin can undergo greater number of exchanges, and greater number of exchanges lowers the total energy of the system and increases the stability. And when it is 1 singly occupied, half filled, what happens? The repulsion is less. Okay, so exchange energy concept I have mentioned. For that reason I have shown here this thing, stability due to exchange energy. See, more number of exchanges, what is happening here? It is how many exchanges are possible in a D4 configuration? Okay, 3 exchange, 2 exchange, 1 exchange, totally 3 plus 2 plus 1 gives you 6. But when you are seeing over here a D5 configuration, 4 exchange, 3 exchange, 2 exchange, 1 exchange, to a total it is 10. So greater is the number of possible exchanges, greater is the exchange energy associated with it. And lesser is the energy, that much of energy is liberated. That much of energy is liberated. Lowering the energy means increasing the stability. See, total number of electron exchanges is larger, which leads to relatively greater stability. Okay, now electronic configuration of ions. When you write the electronic configuration of ions, please remember that for cations you have to remove electron from outermost shell. From outermost shell, you have to remove electron. Now here it is like, though 4s is occupied first, then 3d in case of energy factors, but when you remove electron, 4s is the outermost. So outermost in comparison to 3d, if I'm talking about iron. So there you see, this is iron. Okay, so there if Fe2 plus you say, the first electron will go from 4s, the second electron will also go from 4s because it is 4s2. Now Fe3 plus, after electrons are removed from 4s, then electrons will be removed from 3d. Okay, so always remember that to remove electron from the outermost shell for cations, these are the cations, for cations. And for anions also, always remember that you have to add electron. Add electron where? To the vacant orbital of lowest energy. See, 2p5 in fluorine, it can accommodate maximum 6. So F minus, these are the anions. So F minus can take the last electron in 2p6 only. That means in 2p, making it 2p6. Oxygen has p4 configuration, 2p4. O2 minus will take electron in 2p only, though there will be electron repulsion. because when you add one electron and go to add another electron, there will be energy factors associated with it. Okay, so now this is the condensed electronic configuration. These are the condensed electronic configuration, and that means with respect to the noble gas, nearest noble gas. See, hydrogen, then the noble gas is helium. When I'm writing lithium, then it is given with respect to helium. The next noble gas is neon. So neon is expressed in terms of helium, but after neon, all other elements are expressed in terms of neon. Then comes argon, which is expressed in terms of neon, but after argon, all other elements are expressed in terms of argon. So you have to remember that when you are telling helium, helium means atomic number 2. When you are telling neon and you are writing the electronic configuration, means neon 10. So 10 electrons of neon, and the 11th one you are giving in 3s. So 3s1. Argon has atomic number 18. So when you are writing elements beyond argon, so you have to consider it to be argon 18, and then uske baad if it is 19, then it goes to 4s1. 20, it will again go to 4s2. Till 20 it is over here, and rest the entire table I have given for your reference. Whichever element you need to, you can get it. So that's all for today's session. I think it have given you little bit of concept enrichment, and bye all of you, and all the best for your study. Practice, practice, and practice. Practice makes all of us perfect. So, whatever we have discussed in this session, let us practice as many questions we can of each type from wherever resource, whichever resource you are getting, be it online or offline. I will say do practice variety of questions and explore more concepts for enjoyable learning. Now, you people are tech people, so for them I'll say utilize technology for your benefit, but let technology not use you. You use technology for your benefit, and do explore some new books and use your senses and have the habit of book reading. Yes, book reading is very important in this age also. It gives you observation skill, it gives you patience, and it increases your concentration level, because there you don't have multiple tabs open and distracting you. Read some good books. Bye all of you.